Okay, hold on one second. Okay, we're going to start the final session of the afternoon on dynamics, orbits, and bodies. So thank you, everybody, for reconvening on time. That's pretty good. So our first speaker of this session is Helena Morais, and she will be speaking on high inclination centaurs and a TNO in resonance with the giant planets. So go ahead, Helena.
Okay, thank you. So if you could advance the slide, please. Okay, so why high inclination orbits? Okay, we know in the solar system we have comets on high inclination and retrograde orbits. We have the long period comets and the Halley type comets. The first ones come from the Oort cloud. The Halley type also probably do, but it is not absolutely certain. Next slide. Okay, but there are also centaurs and trans-Neptunian objects with high inclination orbits and retrograde orbits in particular. Next slide. Okay, so we want to study resonances, resonances at high inclination. We already know how do they behave at small inclinations. So in particular, so if we have a resonance of the type P over Q, which is the ratio of the mean motions, we know that in the planar case, when the inclination, relative inclination is zero, the resonance terms look like this. So the amplitude goes with the power of, is proportional to the eccentricity to the power of P minus Q. If we now want to study retrograde resonance, so now the inclination is 180 degrees, this changes. So the retrograde angle is now different, and so is the amplitude of a resonant term. Now we have the eccentricity to the power of P plus Q. So the first conclusion that we have here is that retrograde resonances are weaker than prograde resonances. Next slide. Okay, this is an example of a resonance. So a resonance, this is the center of a resonance, the 2-3 resonance. In this case, it is a prograde configuration. So the inclination, relative inclination is 0 degrees. This is the case of Pluto and Neptune, which are in the 2-3 resonance. So the orbits intersect, but the configuration is stable. On the left, we see the motion in the rotating frame, and on the right, in the inertial frame. Next slide. This is an example of a retrograde resonance. In this case, the 1-2 retrograde resonance. So notice on the right-hand side that the objects go around the sun opposite ways. And on the left is the relative motion in the rotating frame. So again, a stable configuration, but the motion is retrograde. Next slide. Thank you. So this is just another example of the 1-2 retrograde resonance, but now the orbits intersect, as you can see on the right panel. But of course, the objects are never in the same location at the same time due to the resonance. It's a protection mechanism. Next slide. Okay, so why does this matter? Actually, we found out some years ago that there are objects in the solar system in this type of resonances. So we have 3 centaurs, which are in the 1-2 resonance with Jupiter, in the 2-5 also with Jupiter, and in the 2-3 with Saturn. So they all have retrograde inclinations. And we also have an object which was more recently discovered, which is in the 1-1 retrograde resonance with Jupiter. It's a co-orbital of Jupiter, but on a retrograde orbit. Next slide. Okay, if we compute capture probabilities, so in this simulation we have an object drifting inwards towards a planet slowly in a adiabatic setup, and we compute as a function of the inclination of the orbit the capture probability. So we count the number of objects that get captured in resonances. And the conclusion that we have from this work is that retrograde resonances actually capture objects more efficiently than prograde resonances. Okay, the different colors here correspond to different eccentricities. The red curve is for zero eccentricity, and the other ones for increasing eccentricities. So retrograde resonances are weaker, but they capture more efficiently. In particular, you have a significant probability of capture for polar orbits, so polar resonances, which I will talk about in the next slide. Okay, so how do we study polar resonances? Again, we have to compute what are the appropriate resonant terms. And if we do that, we see that now they behave quite differently. Now, not only the resonant argument changes, but now the amplitude of the resonant term goes as the power of the eccentricity to the power of k, where k, if the resonance is even, k is even, and the lowest possible value is 0. If the resonance is odd, then k is an odd number, and the lowest possible values are plus or minus 1. Okay, so in this slide, I show also the comparison for the planar case. So for when the relative inclination is 0 or 180 degrees, the power of the resonant term goes as the eccentricity to the power of q. Here, I show that here at the bottom of the slide. Okay, next slide, please. Okay, so why do polar resonance matter? Actually, we found out there is an object which is in a polar resonance. It's a trans-Neptunian object. On this slide, I show two objects, trans-Neptunian belt objects, which have polar orbits. And one of them, Nico, is in a polar resonance with Neptune, which we'll see on the next slide. Okay, so it's in the 7, Nico is in the 7 to 9 polar resonance with Neptune. Okay, so the resonant argument corresponds to k equals 4. Okay, it stays in this resonance for a while, for some million years. This is just a simulation. The next slide, please. Okay, so now I would like to talk a little bit more about the retrograde co-orbital resonance. Why is this resonance interesting? This is how the motion looks like in the inertial frame on the right and in the rotating frame on the left. So it's a periodic orbit. The configuration is stable in the three-body problem forever. And next slide, please. And of course, now we know there is an object in this type of configuration. It's not exactly in the plane. The relative inclination between this object and Jupiter is around 160 degrees, but the configuration is still stable when you get out of the plane. Next slide, please. Okay, if we now do the experiment of computing capture probabilities in the co-orbital resonance as a function of the inclination, we see that actually the capture, that the orbital parameters of this object, Jupiter's retrograde co-orbital, correspond to a peak of capture probability, which I show here with this red arrow. Okay, so this is the likely state. This is next slide, please. Okay, so to try to find out what could be the origin of this object, we decided to follow 1 million clones. Okay, why clones? Because of course the observations are known with arrow bars. Okay, in fact there is a 6-dimensional arrow ellipsoid, so we want to distribute as many clones as possible within this arrow ellipsoid. So we did that, and we follow the object, the clones backwards in time. We can see on the next slide. Okay, so we follow the clones, taking into account the gravitational effects of the giant planets and also of the galactic tide, which becomes important when they start to get very far from the sun. Okay, and what we see here is that at minus 40 million years in towards the past, there are still quite a lot of objects in Jupiter's orbital region, but the less stable clones start to get out, and as they get out, they move towards larger semi-major axis, and the inclinations start to approach 90 degrees. The next slide, please. Okay, so we follow these. We took several snapshots of the evolution of our clones, and when we arrive at minus 4.5 billion years ago, so at the start of the solar system, we found out, which was quite surprising, that there are still stable objects, in particular stable clones. In particular, there are still objects that didn't leave Jupiter's co-orbital region. Okay, the other stable clones are in the scattered disk, but with polar orbits, and some others started to enter the Oort cloud due to the effect of the galactic tide. Okay, so we arrive to this slide and we make the question, so what is the real object? And what we did here was we invoke the Copernican principle that tells us that we are not observing the system at a special time. So if the stable orbits exist, if they are possible within the arrow bars of the observations, so we should pick those ones, because if we're observing the object now, and if there's a possibility is stable, then we should be observing the stable orbit. But all of these orbits on this snapshot here could not have been formed within our solar system, okay, because they're retrograde or polar. The Oort clouds, the solar formed from objects ejected from the vicinity of the giant planets, didn't have time to form. Hadn't formed at this stage here. Okay, so the conclusion, actually, the next slide. The next slide, what I'm just showing is that this type of reasoning is invoked when in the discoveries of extrasolar planetary systems. So often the best fit, the best orbital fit to the observations doesn't correspond to a stable solution. So of course, in that case, we discard that one and we choose the stable configuration, because it is very unlikely that we are observing an unstable configuration. The next slide. Okay, so the conclusion is that this object would have to be captured. If it could not have formed in the solar system, then it was captured from another star. And why? Because stars form in clusters, and as they are forming and as their planetary systems are forming, exchanges of material can occur. Okay, so now the last slide, please. Okay, this is just an overview of what I said and some open questions, which I left as a maybe. Okay, so we've seen that high inclination centers are captured in resonances. We also saw that retrograde and polar resonance are different from prograde resonances, and that retrograde and polar orbits are captured more efficiently overall in resonances than prograde orbits. Okay, I just leave the open questions for you to read. Maybe I just point to the last one, that the origin of these objects is still an open question. Okay, that's it. I hope it was clear. You could hear me well. I do not seem to hear anything, but my talk has finished.
Can you hear me?
And now I can.
Can you hear me, Helena?
Yes, I can. Now
Okay.
I can.
Thank you. Good. So we'll open up for questions now. We just have 1 minute.
Okay. Very nice talk. This is Luke Doan, Southwest Research Institute. I mean, this is very nice work. However, I do have a question about your capture scenario. It seems to me that you could also have objects coming back from the Oort cloud, getting, caught into this retrograde, Trojan orbit for a short period of time, maybe 10 to 6 years or something. And so you just kind of have one at any given time, as opposed to one object that's just been there for the age of the solar system. Could you comment on that, please?
Yeah, okay. Well, our philosophy was completely different. We're not trying to capture anything. We just follow clones backwards in time to try to see if we could figure out a possible source. If we didn't find stable solutions, and particularly stable solutions which didn't leave the current state, they stay at the current state for all of this time, then we couldn't conclude anything. Okay, but I think if you have a stable solution, why do you want to go and choose the unstable one? Maybe it's a philosophy argument. But we didn't try to capture anything. There is no capture mechanism here, okay?
Okay.
I hope it was clear.
Thank you. Let's thank Helena once more. And then do you know how to switch to the next talk? I'll disappear. All right, our next speaker will be Rodrigo Leiva.
Is that good enough? Yep. Okay. There is a version. There is A and B. I think the B just I did some typos correction. Right? There's yeah.
Did you upload another one?
Yeah, just say B. It's just a small changes.
No, then I need to download it.
Okay.
Okay. So.
Sorry for that. Oh, I can use that. It's just it's a small typo.
Is A fine?
Yeah.
Okay.
It's nothing fundamental.
Okay.
Yeah, sure.
Well, I'm going to ignore the typo.
Yeah. If you find the typo, you can
We'll
eat
just
some
ignore that.
extra.
Yeah. Okay.
Fruits.
Thank you. Okay.
There are two.
Okay, we'll ignore 2 typos. Anything beyond that, we can point out. All right. Rodrigo will be speaking about scenarios for rings among Centaur objects. And this is your clicker, and I'll give you a 10-minute warning.
So is this one here? Okay, so the motivation of this is, as you know, and was mentioned before, we have a couple of small objects, and the only one so far that we are sure that we have rings around. Chiron is a suspicious object, but I'm not including that one here, but will be mentioned later. So it's essentially Chariklo that was discovered in 2013, and Haumea more recently, a couple of years ago. The main difference of the rings of these objects with big planets, I mean, the giant planets, is that the central object is not axisymmetric in the potential. So there is a fundamental question there. I mean, the fundamental difference there that I will mention more after. A detail in the rings of Chariklo to keep in mind is that it's not a single ring, it's a double. And this is one of the best data set in the discovery. There is a clear gap in between, and was seen in the entrance and exit. And there was several occultations later. As Amanda mentioned, if you have one occultation, that immediately improves the orbit of the object, and you have the chances to have more. And the case of Chariklo was crossing the galactic plane, so we have a lot of opportunities to observe more. And one in particular, this is 1 year later, you can see that there was a model here to try to put a number in how sharp was the border of the rings, and this is the main ring. And this 1.5 kilometers is this measurement, is modeling the ring in 2 steps, and actually it's very sharp. Can be detected with the resolution of the occultations. This is much better resolution than the discovery. And so it's very sharp. This is 1.2 and this is 1.5 kilometers. So that is something that also is important to keep in mind. This essentially is telling us that for sure there is some mechanism there confining the rings. So this could be the simplest model that we were thinking. There must be a satellite out here, could be very small, a couple of kilometers, another one here in the gap, and another one confining the other small ring. There. So later, this is putting together several occultations where we saw the body. So as you see, there are some mapping the upper part, the lower part, the center part, the more diametral, and a combination of those. And we were able to constrain very well the shape of Chariklo. And this combined also with light curves in a similar approach that Estela was showing before. I mean, we have historical absolute magnitude of Chariklo, and also a few light curves where the amplitude was detected. And putting all that together, here I tried different models, but the one that makes more sense is just a general ellipsoid. And we can see that it's quite different. This is the polar semi-major axis. So it's a very flattened object and also very elongated. So why is this important? This seems like just a little difference. But actually, if you compare that with a spherical object that is homogeneous, there's a lot of mass, extra mass there in those lobes. Also, if you compare this nominal model and you see the length of the chord, you can see that we were able to measure the typical size of the topography of the object. And it's not minor. For this model, it's about 6 kilometers. So there is also some extra mass there. Even in the case of a spherical model, a spherical object, we have some dispersion with respect to the nominal body. So there was a work published last November with my previous advisor. What is the main effect of these two pieces of evidence of the body, the elongation and excess of mass? So the simplest model is to consider that these are dependent only on longitude. There is no dependence of the latitude. And we put some material in the equator without even asking very much how the material reached there. But in our case that we are focusing in Centaurs, we have a possible pathway to put material there that this could be activity. So what happens if you put material in the equator is that the resonances between the spin of the body and the spin of the particles around will, in a very short time scale, this is for the dimension of Chariklo and assuming a reasonable density of 1 or 0.8, I think, I don't remember exactly this integration. The arrows should have a text here, but this is roughly where the co-rotation radius is. So everything that is around that co-rotation, the result is that it's clean. So all this material quickly goes to the object. there are several resonances here, and the material outside of the co-rotation also is pushed away. So this is the case of the elongated body, but in the case of the excess of mass, I mean, considering it's a very homogeneous object, it's a spherical, homogeneous density, and you have an excess of mass of the order of those 6 kilometers, you will have a similar effect, chassis is lower. So in both cases, there is a gap. Here I put the resonance 1, 2. And in the case of the elongated body, actually the gap is slightly outside that. But I put this because it's generic for the two cases. So what is the extra piece of evidence? We have not only the rings, possibly we have these satellites confined in the rings because are very sharp. And we have this gap that was detected in several occultations for 4 years at least. So for a given density of the particles, you will have a radius that is the rush radius. Actually, this is a kind of a zone. And for a given rotation period of the main body, in the case of Chariklo is 7 hours, this gap will form in some location. So if this is well outside of the rush limit, what is expected is that this will just form some satellites. And if you change the rotation of the body and you make it faster, this will start to move inside. And at some point, the rotation period of the body will make this gap match roughly with the rush limit. So when we did this experiment, put in some values, we know the rotation period of Chariklo, but we don't know the density of the particles. But we did the opposite experiment. What is the density necessary to have this configuration? This is something reasonable, something 0.5, 0.4. So it's not crazy high or crazy low density. So in this scenario, you could have that some of the particles that were pushed away very quickly can aggregate in satellites, and others will just keep as particle of those, and this will be responsible to confine the other ones. So actually, this is what happened around the rush radius. Is not a sharp limit, so there is an area where both things can live together. And actually, I didn't put a figure thing, no. But when we put the values for Haumea, it's something similar. I mean, assuming the reasonable density for the particles of the ring, the gap that is formed under this scenario is roughly where the rings were detected. So this is a very simple first approximation of what could be the pathway to have rings there. We are not answering the question how the rings form, but once you have material around, this could be the pathway to explain why the rings were not closer to the object. So because it's essentially not possible. That area is cleaned too fast. So the motivation is now, okay, when the object is rotating fast enough, it's possible to have this scenario. So actually, this is the same that was shown in the morning, I think. The same plot is from JPL. Around 20 Centaurs with a known rotation period. And Chariklo actually is this one. And have rings. This is Chiron. It's also in the fast part. Maybe have rings. That's why it's yellow. And this is one that was measured last year. I think the publication is in process. But I'm not sure. I need to see when they published the result, if the sensitivity was enough to see rings or not. But actually, there are not too many fast rotators. This is maybe not the fast rotator in the same category that were mentioned before, but under this scenario, these are the fastest. So these are the only ones that actually we are sampling with occultations, which is the only technique able to detect these rings. So the thing is that if we start to go higher, the density of the particle necessary to have this situation where the rush limit and this gap are close, it starts to be unrealistically low. So only a fraction of these objects could have rings in this scenario. So what happened in 2013, we were not looking at rings at all. We got one just by chance. And we said we have only one, a dozen of objects, and one we got rings. So maybe they are everywhere. But actually, it seems that it's not that easy. So maybe we're lucky that we were observing a large one that was easy to predict, I mean, compared to others, and was a fast rotator, so maybe wasn't the right position in this plot. This is just the size to have the rings. The thing is that we only have this 20 with rotation period. So the idea is, what is the full picture of this? How many more objects? These are the easy ones to detect with a couple of meter telescope, maybe 1 meter telescope. But this is something like 10% or maybe less of the known centers. So we need to see what is the full picture here if we have more in this area. This one actually, I don't remember the name of this one, but it's still in the range of 100 kilometers, something like that. Maybe it's more. So I tried to put what was suggested to put open question, and I was thinking, okay, I will try to do something, but all of this was already mentioned before. So maybe my initial reasons to get more about the rotation period of Centaurs, if I was thinking, okay, maybe we can focus then, if we know better, we focus in some few occultations and to find more rings. And we will try to figure it out. What is the real pathway now for the formation itself? Because this is just, we are avoiding the big question, why the material was there, but maybe in Centaurs, the link is in the activity. So this is more like a suggestion, and that we need, of course, more data, but why and what specific data? More likers. Because this also will give us a secondary information that is linked with the shape. If we have an object that we cannot detect rotation period, it's also telling us something that is maybe more roundish. Will not be a good candidate for this scenario again. Just to have an idea, this is my last few seconds. We only need, if we have a perfectly spherical body and totally homogeneous, we only need something like 4 or 5 kilometers mountain, if you want to call it like that, to have an effect like this. I mean, to clean this material in the scale that is relatively short. I think we estimated with 5 kilometers would be something 10 to the 5 years to clean this area. So it's still a good scenario. So the regularities to explain this is just very small. I think I will stop there because it will be more interesting to talk about it. Yeah.
Thank you very much.
Okay.
Okay, we're going to open up for questions now.
So this is Julie from FSI. So I'm sorry, I did not understand the whole Roche limit story. So why so the ring is moving towards the Roche limit if the parent body is rotating faster?
Well, the Roche limit where it is depends on the particles that you consider. If you put lower or higher density.
Yes.
So let's consider just a fixed density will be some position.
Uh-huh.
So then if you consider different rotation periods for the object, this gap that was because of the resonances will move. So it is not a ring moving, it's just where the gap will be for different objects rotating at different speeds. So if you have a faster rotator, the limit will be there.
Okay, thanks.
Yeah. So that's why this part of the plot in the rotators is more interesting, because you have that situation. Otherwise, there will be no chances to keep rings. Everything will be coalescing in something like a satellite or multiple satellites.
Thank you, Rodrigo.
Yep.
Gal, Sarid, FSI as well. You're mentioning the fast rotators, which immediately made me think of Julie's talk.
Yeah.
She mentioned the advantage for the mass shedding mechanism for fast rotators.
But I don't know how fast are yours compared to this anyway.
I don't know. Fast being something.
Yeah.
but there is a limit with the size of the grains that are connected to that, to the efficiency of the mass shedding. Do we have any idea, or how can we get a proxy for the size of the particles
in the
ring?
surface or in the rings?
Yeah.
Well, the more direct way is to try, actually when an occultation will be to have two different wavelengths. And if the typical size of the particles is, well, you can infer with if you see the same drop, the same amount of drop in the two light curves in different wavelengths. As it's different, you can try to infer the typical size, assuming that there is some kind of slope that is dependent of the wavelength. We did only one experiment like that, but actually it was between the visible and the near infrared, something like H-band, I think. A couple of years ago, 2017, I think. There was nothing detectable in the signal to noise ratio that we had. But I think it was not good enough. But that will be the kind of experiment that you can do from the ground. A very bright star and big aperture to have good signal to noise in two different wavelengths, but well separated. Is this what
Would
is
you
that?
like to guess? I mean, what's
What
your
is
favorite
typical
number
size?
for the size of a?
I have no idea. No.
Okay.
Matthew Knight, University of Maryland. So along the same sorts of lines, I'm wondering about solar radiation pressure. Are there certain sizes of grains that would just not be capable of staying there? Have you considered that?
No, here we didn't consider any of that, or radiation pressure or shadowing of the object now. So there's only the gravitational potential of the body. Anyway, yeah, it's possible that the radiation will clean some size ranges. I was thinking also at some point, which we didn't study in detail, maybe we will do it, is how the radiation will influence the dynamic itself. But actually what we think is that this is already confined. So it's more relevant, the putative satellites that are there, confined in the rings. So for this part, maybe it's not relevant, but maybe for cleaning some range of particle size, yeah, it could be relevant. But
this is far from the sun.
13 to 18, I think, is astronomical unit is the range of Chariklo.
Yeah, I mean,
But just
yeah, I mean,
yeah.
Yeah.
The radiation pressure drops like r squared from the sun, and so does the gravity. So it comes out independent. Read Joe Burns' paper in Icarus, January 1979. He wrote a poem about this. It's like a 70-page paper about all the radiation effects.
Yeah, there are some drugs effect that could change eventually the dynamics and spread the ring. But when you put confinement, all those start to be just secondary effects. But still could be some effect in what is the distribution of sizes that we don't know in this case. Anyway.
So Julian and Alan, and then we need to move on.
okay, this is just from this earlier what we were talking about. So it's easier to lose large grains from the surface than to lose small grains. Oh, sorry. It's easier to lose large grains from the surface than small grains. So I guess you would preferentially have at least, I mean, not the very fine stuff is very sticky. So you get these fast rotators that, are still have, that do not, what was the name of this body? That does not split apart, even though it's actually such a fast rotator. It's probably because it has fine grains in it. So I'm just saying that like from my feeling, I would see more of the not too fine stuff spilling anyways. Okay, and so my question was, sorry, yes. My question was, when you started putting material around the body in your simulation, did you have a preferential equatorial distribution?
This was totally equatorial. There is no longitude. I mean, there is no latitude effects. So all the resonances.
So this would have to be a process that would inject material equatorially.
Or something to put. Yeah. Yeah. Eventually we'll.
No, because I think that like Dave Minton from Purdue, he made some simulations. Can you trap material in a ring that comes from impacts that are isotropic? And because it was so isotropic, he was not able to capture enough material. in a ring. So from what he saw, he would have to have some sort of equatorial distribution beginning.
Actually, I don't have the answer for either with the activity, how you put material in the equator to start with. But I put that as an open question. I mean, it's actually I would like to explore eventually. This is just, okay, there is a big disconnection there. You are putting material around, and if you manage to put that in something resemble a disk, then this old order effect will take care very quickly to put the material in the right position. But, yeah, the thing is that the time scale is the tricky part. That this is very fast, so you need to have something that is faster than that. Yeah. Otherwise, you will need to deal with the more complicated case of material all over the place. Exactly. Yeah. Could be analyzed eventually.
Okay, Alan Stern, Southwest Research. Chiron is a particularly interesting case because we know it also has gas, and gas creates gas drag, which is an important loss process to small particles. And there's some interesting story that Chiron is telling us, I think, about something about either the lifetime of the rings or how long it's been at lower heliocentric distance to support this atmosphere. And I think that's a fruitful area for some work.
Here's your simulation of the gas dynamics.
Here. Thank you. Let's thank Rodrigo again.
Well, this would be for series, starting with the froth on the surface, and you can show how it.
So, the next person is online. Should we online?
Yeah, B version, right? Winter?
Okay, how do you pronounce the first name? Othon? Are you online?
Yes, I am.
Winter, you should be unmuted. Can you hear us?
Yeah. Can you hear me?
Yes.
Sure.
How do you pronounce your first name, please?
Autumn.
Othon?
Yeah.
Okay.
That's good. That's good.
All right. Okay, we're ready to go here. Are you ready?
Yes, I am.
Okay, one moment, please. So our last speaker for this session is Othon Winter, and he'll be speaking on the connections between Chariklo's shape and its rings. Okay, so I will advance slides for you when you tell me when. Okay.
Thank you. Well, so this work we discussed some aspects, other aspects of the rings, and some possible connections with Chariklo. Actually, this is a first model, so we still need some improvements. I'm going to discuss that at the end of the presentation. Next slide, please. So I'm not going to talk much about this motivation. Rodrigo showed that before. The only thing to say is this last line where both Chariklo and Haumea rings are near the 1 to 3 resonance with the body. So Chariklo gives around 3 times, while a particle of the ring completes one cycle. Next, please. So in this work, we are a little bit concerned about the shape of the bodies. So in the case, we are going to talk about Chariklo especially. But if you think about an ellipsoid, so you have semi-axis A, B, and C. And from that, you can define in these 2 parameters the oblateness and the ellipticity. So the ellipticity is the elliptical shape of the equator of the body. And so in the case of Haumea, that seems to be quite well defined with good precision. And but in the case of Chariklo, there are several possible solutions for the occultations found up to now, as was shown in the previous presentation. So we will try to make some connections with the shape of Chariklo and some possible using some information from the rings. So next slide, please. So I'm going to talk with three main concerns here. So first, what is the orbital effect on a particle when you take into account the ellipticity? And the second one is using that effect to estimate. It's a simple estimation, but it's a first estimation for some limiting shape of Chariklo. So what would be the limiting value for this ellipticity for Chariklo? And the third aspect is concerning about the 1, 2, 3 resonance. So is it is it important or not with the ring location? So how close is it to the ring location? So let's move on to the next. So if you take a simple two-body problem with a body like a Chariklo mass, and you take into account just the oblateness. On the left, we have the radial evolution for a particle that started near circular. So the eccentricity, despite we getting very small eccentricity, the eccentricity grow several orders of magnitudes due to the J2 effect. If you consider the plot on the right is just considering the ellipticity, and it also produces a similar effect in terms of growing eccentricity. So next one, please. If you think about J2, that's a well-known problem. If you start the particle with a velocity, assuming a Keplerian problem, but the body, the central body is oblate, if you try to put a circular orbit with the velocity, you are not going to get a circular orbit. It's going to produce an eccentricity due to the oblateness. So that problem has been studied a long time, and mainly for bodies near Saturn, near the rings or close to Saturn. And the idea is that you should consider an adaptation of the orbital elements to what is well known as geometric orbital elements, and that would correct this effect. So then you could give the right velocity to get a circular orbit. Next one, please. So here we have the same example shown before. So in yellow, we have the evolution considering the velocity from the two-body problem oscillator orbital elements. But if you use the geometric elements, you get the blue dashed line that keeps the eccentricity very close to zero. So you get a circular orbit. So the next slide, we start discussing now what happens with the ellipticity. Well, the ellipticity is not exactly the same as the oblateness, because you get an azimuthal asymmetry, what does not happen with the oblateness. And this asymmetry is going to produce a minimum eccentricity. So the question is, can we find geometric orbital elements for that? The answer is no. We cannot, because you will always have some distortion due to the asymmetry, azimuthal asymmetry of the ellipticity. Next one. And here's the example. In purple, we have the initial conditions considering oscillating orbit, and the variation, radial variation is significant. But what we can do is empirically try to change the velocity and get the minimum amplitude of oscillation. And that is what happened with the blue line. So we found the minimum radial oscillation, but we can never get it equals zero. Does not exist a circular orbit around a body with ellipticity. So the ellipticity produces this minimum eccentricity. So if you get in nature, it goes to, usually when you think about rings and particles, it goes searching for the minimum eccentricity. And so if possible circular, but in this case, it's not possible to be circular. So we are going to use this information. It's a correlation between the orbit of a particle around an ellipse, a body with ellipticity, and the value of this ellipticity. So there's a correlation between this value and the radial range of oscillation. So we try to do that, and in the next plot, we have made that for several values of this ellipticity on the x-axis, and found the range of the radial oscillation for the minimum oscillation possible. And this is for the case of a Chariklo-like body, and near the one of the rings, the smallest one, the outer ring of Chariklo. So if we have a ring, if that ring has a radial range around 1 kilometer, we have this C22 value that has to be at the most 0.0133. And if it goes up to 3 kilometers, it's going to be about 3 times this value. So, and from that we can get the shape, or some information about the shape of this body of Chariklo. But we have to keep in mind, this is a first model. We didn't take into account collisions and some other parameters that has to be considered. So in the next plot, next slide, we have here a bunch of values. So assuming one of those 2 values of limiting values for 1 kilometer and 3 kilometers, of the value of the ellipticity, and for different values of the oblateness, we got some range of values for the A, B, and C semi-axis for Chariklo. And that we can show that in the next slide. Just, I'm not going to discuss, but just to show that there was a range of possibilities fitting the occultation data. And so we can impose some limits. As I said, it is a first model. But if we consider that if it is a good model, we could eliminate, for instance, the Jacob ellipsoid solution. But as I said, we have to take that with care. So in the next plot, now I'm going to discuss a little bit about the region where are located the rings and the resonance 1 to 3. So I'm going to use the Poincare surface of section. So here we have an example, and just for those of you that are not familiar with that, these islands correspond to islands of stability. And at the center of the islands, usually you have a periodic orbit that is very stable. And so the size of the islands, the location of the islands, and the equilibrium points inside them give some information about the stability of that location. And so here we are dealing, the value on the top of the plot corresponds to the Jacob constant that is actually a kind of energy of the problem. And so here we are showing one surface of section where appears the 1 to 3 resonance. It appears doubled. So there are a pair of solutions. So if you take the 2 green islands, it's one solution, and the 2 purple islands is another solution. So that's the first important information. So since we have 2 solutions, it actually divides the space in 2 parts, so making the stability around the 1 to 3 resonance much smaller. So it's like breaking a stable region, 2 small regions with chaotic regions between them. So that makes this resonance much weaker than the actual what could be expected. Formally, this resonance could be thought as the 2 to 6 resonance. So it has another order of magnitude, much smaller. And I wanted to comment this red island in the middle that has nothing to do with the resonance. There's another type of periodic orbit, but it calls our attention because it's much larger than the resonance 1 to 3, and they are in the same region. So in the next plot, next slide, there is a set of Poincare surface of sections. The idea here is just to have an idea of sizes. So I don't pay attention about the values, but just the size. So if you see the first plot in the left corner, top left corner, we have the green and purple islands associated to the 1 to 3 resonance. And then they start going to the other plots, they start growing and getting closer to the center of the red island. As you get to the last plot on the right down corner, they almost disappear in the middle. But the interesting thing is that the red islands survive. So only in this range of energy, Jacob constant, exists this 1 to 3 resonance. But while these red islands exist before and continue afterwards, and they are in general much larger. So in the next plot, next slide, sorry.
1 minute, Oytan.
Okay, so here we have what can be separated into 1 to 3 resonance and the center one. Poincare has studied this orbits 100 years ago. So the right one has to do with very close to zero orbits, eccentricity. So near circular orbits. Next one, please. And so in this plot, we have a semi-major axis eccentricity. And in blue and green, we have the location of the rings in terms of semi-major axis eccentricity. And the line, or purple line on top, is indicated the location of the resonance 1 to 3. And the red line indicates the other red islands. And it shows clearly that it's much more likely that the stable region is dominated by the red islands and not by the 1 to 3 resonance. Next slide, please. So here are my final comments. So the ellipticity shows that there is always a minimum eccentricity. And using that with Chariklo, I use commas here to indicate that the shape could be limited depending on the size or the width of the rings, of the inner ring, the outer ring, the smaller one, the narrower one. And in the last line, the ring region is mainly dominated by this central periodic orbit family, not the 1 to 3 resonance. And the last slide. So there are plenty of things to be done, but we have some parameters that are crucial here, as the mass of Chariklo, that changes quite a lot, the power of the resonance and all the other effects associated to it. And the effects of collisions has to be taken into account. And a confining mechanism also has to be considered. And that's our next step. And it would be interesting to hints about if we are lucky to have a occultation that, by the way, could get a molet. So that's it. Thank you very much.
Okay, thank you. We're opening up for questions now. So I'm gonna go.
Rodrigo Leiva, Southwest Research Institute. I was wondering that actually in the second line that you have there, the shape, we are quite close to what the shape is given the occultation. So actually you will be limiting the mass distribution perhaps of the actual gravitational potential of the object. Can you comment a little more of that? Because it seems like deceiving that we will limit in the shape. Actually, we know roughly the shape.
Yeah, well, if assuming that our model is reasonable and that the ring has a width of, the narrower ring has a width of about 1 kilometer, the elongated shape, the C22 parameter would be smaller than the one of those presented in the table of Leiva, sorry, your colleague. So what I mean is that the mass is important. So without the mass, it can change these results somehow. but also in having the same mass we use it and from your work, the work of your group, the shape has, let's say, a stronger limit now. It's a little bit stronger than the one presented in the paper. The paper is wider options.
Thank you. Gal Sarid, FSI UCF. So I think in Rodrigo's talk, you showed maybe a telltale sign of sharp edges to the rings, which can constrain the location and presence of moonlets. And so I'm wondering if any of you, or you want to check that together later, if you put the moonlets in a location where they confine the rings, how does that get affected by the ellipticity of the central body? Because that would affect the stability of these moonlets.
Yeah, certainly. One thing that I can say straightforward is that this moonlet would have this minimal eccentricity. So that keeps the ellipticity affects the eccentricity of the moonlet. But it's I cannot say much about what would happen to the ring particles because that is a more complicated combination. So that's our next step in the work. So take into account the confining mechanism together with the shape of the body. But one thing that's for sure is that the eccentricity of the moonlet would affect the ring anyway.
Okay, thank you.
Let's thank Leiva again.